Okay, so let's do it. Series and parallel, voltage and current. We're also going to talk about
Recording in
resistance,
progress.
which is not futile. It's V over I. Hey. So first off, I would like to define the terms, the new terms that I'm going to give you. I'm going to give you a little table. Then we're going to spend the entirety of the class diving into what and why and how and where. But make this table. This is the core of the class, the core of today's lesson. I want you to understand what series means and what parallel means. How to identify them. Things are in series if and only if direct connection with no junction. You guys know what a junction is? A split, an intersection, a T, some place where a third wire comes in. Things are in parallel if there's a direct connection on both sides. And no intervening parts. I can spell. You guys know what intervene means? No intervening parts. Oh, for God's sake, let me spell it correctly. Intervening. Something is intervening if it's getting in the way, if it's interfering, if it's blocking, if it's between. Okay, so here's how to identify series and parallel. Now let's talk about the principles that we're going to be exploring. Voltages in series add up. Voltages in parallel are equal. Currents in series are equal, and currents in parallel add up. When we talk about the why, this is true constantly. And then moreover, there's a formula if I've got resistors, and only if I've got resistors. Let me say resistance. I just add series resistors. And then there's a god-awful formula. Whoopsie, not that. Which could be summarized as saying, take the reciprocals, add them, take the reciprocal. If you deeply, truly understand this table by the end of the day, I will be very happy. I will be very happy. Tomorrow's my birthday, by the way. Give me a birthday present. This is your birthday present to me. Yeah? Thank you. It will be if you understand this. If not, I will shed birthday tears. The first class, the 3 o'clock class, I was very, very smug, by the way. Their self-reported assessment said on average is about 4 out of 5. 3.8 out of 5 for self-assessed understanding. Hey, let me ask actually right now, Google question A for the people who have, how do you feel you understand voltage and current in particular? What do voltage and current feel like to you? Out of 5, 1 is you can't tell them from position. 5 is you really feel that you have an intuitive and quantitative understanding. Know the equations, blah, blah, blah. Okay, Google A, peaches and daisies. Wow, that's amazing. 3 out of 5, great. Let's see if today boosts that. That's the goal. Okay, so now what does this mean? First off, let's talk about the identifying them. Let's see examples of things that are in series and counterexamples of things that are not in series. And same with parallel. Did you all have that little table written down? I swear I'm going to post these slides, these lecture notes for realsies. I know I say that a lot. I mean it this time. If I don't post these lecture notes, I give you guys full reign to send me 105 emails and tell me, post the lecture notes. Examples. 2 ohms, 2 ohms, 8 ohms. Symbols, by the way. No, not that kind of symbol. Symbols. The squiggle is a resistor. Almost all of y'all should have seen this in the lab last week. There's a new symbol today, and that is squiggle. a tilde on the end of, an enye on the end of a line says, there's more circuit this way, I just am too lazy to draw it. Or it's not important and I want to emphasize that we're focusing on this, yeah? Okay, so here is a fraction of a bigger circuit that we're going to analyze. These are in series. Let me give a counterexample. No two components are in series in this chunk. Why not? Because there's a split. Current that enters here does not have to go into here. It could go backwards through here. Current going this way, perhaps, has a choice. It could go through there, or both. A little bit goes into top, a little bit goes into bottom. Current splits, not in series. Incidentally, the fact that there's no choice, current has to be the same is, oh my God, this principle up here, currents have to be equal in series. How I say this, how I think of this internally is what goes in must come out. If you've got a series, what goes into the one must come out of the one, must go into the next, must come out of the next, must go into the last. Okay, so suppose I've got 2 amps flowing into this first 2 ohm resistor. How many amps flow through the 8 ohm resistor? Google form B. How many amps are in the 8 ohm resistor? Can you find this out? Yeah, if your Google form doesn't work, don't worry about it. I'll give everyone free participation points. But if it does work, answer me these questions so I can see. If it does not work, just focus on doing your notes. Okay, again, the question here, Google form B, if your Google form is working, is how much current flows through the 8 ohm resistor if 2 amps flows into the first resistor? And the correct answer is, as I just said, the current is still the same value. It's still 2 amps. 2 amps flows through the first, that same 2 amps flows through the second, that same 2 amps flows through the third. Yeah? Now, picture this. Picture this. Got a row of students. I'm going to pass test papers down the row. Don't worry, I'm just making this up, no test today. I pass some papers down. He hands papers to him, hands papers to her, hands papers to her, hands some papers to him. Yeah? Say 5 papers are passing down the line. So he handles 5 papers, she handles 5 papers, and he handles 5 papers. Does that mean there are 15 papers? No, it's the same papers, right? If he's passing 5 papers along, and she's passing 5 papers along, and she's passing 5 papers along, there are 5 papers. Now, tell me this, if 2 amps enters the first resistor, then goes out it, and then those 2 amps flow through the second resistor and then goes out it, and that rate of current flow is flowing into and out of the third resistor, is the total 6 amps? No, it's the same amps, it's the same charge, it's the same electrons flowing through. So when I have currents in series, do not add them up. They are the same things that are flowing. By the way, this is not just true for resistors. This is true for any time you have any 2 components. You could draw little boxes and say fill in the blank here. If there's one entrance and one exit from each box, and they're connected entrance to exit, the currents are all the same. Suppose there's 2 amps flowing through here. Are there 2 amps here? No. Some amps are in there and some amps are in there. Maybe this is, I don't know, half an amp there. If that's half an amp, how much current is in the top left? 1.5, yeah, 1.5 amps. Right? Principle about current that we discussed on the very first day of current. Current is measuring the flow rate of stuff, gosh darn it. That stuff doesn't appear, it doesn't disappear. What goes in must come out. I have to have 1.5 plus 1.5 amps going in if 2 amps are coming out. Are these amps the same amps as this? No, they're different electrons. They're different charges. Hey, what about here? How much enters on the far left? 2 amps. 2 amps enters, 2 amps splits. Some fraction, 2 amps recombines, blah, blah, blah. Yeah? Now, it's also possible that the currents might be numerically equal. Suppose I've got equal resistances, then they'll split without loss of generality. They'll split into equal amps. Are those amps the same amps? I mean, the numbers are the same, but do they represent the same things? No, they are different electrons. Alice electron goes through the top, Bob electron goes through the bottom. Alice does not go both through the top and the bottom. Alice and Bob together are going through the right sucker, though. Yeah? Here's another counterexample for not series. So the previous example was we had a parallel junction. Here, this is neither series nor parallel. Nothing is in series here. Nothing is in parallel. Why? Because you got a junction. Current has a choice. We all have a choice. That's very inspiring. But that's the essence of series. Series doesn't. 1 amp goes in, 4 amps come out. What must be in the third wire? Google form. 1 amp flows in, 4 amps comes out. What must be in the third wire? Google form C. Show me you're awake. Again, if your Google form is not working, chillax for a mo. Great, Google form D, up or down? Is current flow up or down in this? All y'all correctly told me 3. Now does it go up or down? Oh, so far so perfect. Oh, so good. Oh, birthday present achieved. People are getting things right. I love you so much. Correct answer is up. If you've got 1 amp going into this point and 4 amps going away from this point, well, where did the other 3 amps come from? You must have 3 amps going into this point and 1 amp going into this point if you want 4 amps to come out of the point. Turn to your neighbor and express a little bit about, this is called current conservation, and what we've seen about series so far. Then I want a question. Turn to your neighbor and discuss. You have 1 minute. Thank you for being here. I was intentionally very boring in those. Well, yes. You won't actually have a circle in this left combination. Not unless there's a magnetic field changing somewhere. Well, that's late in the semester. All right, that's about a minute. That's more than a minute. Give me a question. Someone shout out a question. Ask for clarification. Somebody has a question. We're early on. I could be the greatest teacher in the world and still, this cannot possibly be perfectly clear to everyone. Really? No question? Please, Jane. How is the voltage positive? Oh, we haven't talked about voltage yet. Do you mean how is the voltage adds up to a total? Let's talk about that. This plus sign doesn't mean voltage is positive. This plus sign means voltages add together. So, for instance, let's look at this. Suppose I have, I don't know, a volt here. No, that's impossible. 4 volts here, 4 volts here. What can you tell me about those 4 volts? Are those the same 4 volts? Alice electron flows first through the left resistor, then through the center resistor. She burns 4 volts of energy in the first resistor, 4 volts of energy in the second resistor. Are those the same volts? Is that the same energy? I mean, it's the same numerical amount, but the identity of them. No, they're different volts. These 4 volts and these 4 volts are different volts. Burn 16 volts here. V equals I times R is where I'm getting these numbers. Okay, yeah. These voltages are not all equal. What can you say? What's the total voltage? How much energy must you provide each coulomb of electricity that flows through this? You have to supply 24 volts worth of electricity to get the electricity to flow at 2 amps through the circuit. Yeah, you have to be supplying 24 volts. If there are 4 volts lost here, 4 volts lost here, and 16 volts lost here, you must have given it 4 plus 4 plus 16 at the beginning relative to the end. So voltages add to a total in series. What about the fact that Alice electron is going through the top resistor and Bob electron is going through the bottom resistor? Alice and Bob are both 1 amp. They're flowing at a rate of 1 amp. Remember this example a second ago? Tell me about their voltages. They start at the same point, they end at the same point, right? They start over here, they end over there. Does Alice lose more energy or Bob? It's the same. You start at the same point, you end at the same point. It's the same volts. So if there's, I don't know, 3 volts difference on this guy, there's 3 volts difference on that guy. Does that mean the total is 6? No. By the same, I mean really the same. I'm 6 feet tall. Another person is 6 feet tall. We stand next to each other. The difference between my toes and head is 6 feet. The difference between her toes and head is 6 feet. It's the same 6 feet, right? Would we say that the total is 12 feet? No. The difference between our toes at the same level and our head at the same level is the same feet. Now, if she stood on my shoulders, then our total series voltage would add up. This is a parallel little slice of a parallel circuit here. In parallel, voltages are the same. They're identical. It is the same voltage. Voltage is, whoa, sorry. Apologize if that gave you vertigo. Voltages in parallel are always identical. And you don't add them together in parallel because it's the same stuff. Okay. I want to show what? What do I want to show? I want to show you the way. I want to show you parallel. Parallel. Each of these 3 resistors is connected on the top. Each of these three resistors is touching on the bottom. This is parallel. Not parallel. Well, the right branch is not parallel. These 2 are still parallel. They're touching on the top, they're touching on the bottom. But these resistors, well, let me focus on just 2 at a time. These 2 resistors are not parallel. They might be drawn side by side, but that don't mean nothing. It's not the geometric arrangements of vertical, horizontal that makes things parallel. Makes it parallel if they're connected by wire. There's a wire path that goes from top to top. There is not a straight wire path that goes from bottom to bottom. Question or stretching? Okay, so here's an interruption. Here's an intervening component. This breaks parallelness. Are these 2 in parallel? Yes. Are these two in parallel? No, why not? They are in series. It is possible with one example to be both series and parallel. Series and parallel aren't opposites. You can be both or neither as well. These two are not in parallel because look at they're connected on one end, but the other ends are not connected by wire. The other ends have resistors in between them. You see that? Any path you use to connect this end of this resistor and this end of that resistor is got a resistor in the way. Like this? Like this? That's now those two are, well, no, these combination, these are in series because they're connected without a junction. These are also in parallel because both ends are connected with wire. Also, this is totally pointless because if electricity enters here, nothing is going to flow through these two. But this is a combination which is both series and parallel. I would also call this a dead short. All the electricity is just going to go through there. Yeah. Good question. Okay, so let's say parallel, not parallel. Let's say that, I don't know, 1 volt is dissipated here and 1 volt is dissipated here. The people who are able to Joule in Google question E, how many volts here? And if you can't Google question, write it on your paper. Okay, so again, I've got 1 volt and I've got 1 volt. Are these in parallel? No, they're not in parallel because their far sides aren't touching through wire. Far sides have something intervening. Are they in series? Yes, these are in series because they're touching and there's no junction here. Memorize these rules, by the way. Memorize these descriptions and check every darn time you do a problem. It is a common goof for students to skip over the checking. And if you misidentify, you're guaranteed to die. Your problem is guaranteed to die. You cannot get it right if you misidentify what combination you got. Okay, so if this is 1 volt here and this is 1 volt there and they are in series, what do you know about the voltage? The total voltage loss. 2 volts. 2 volts difference between this point and this point. How much voltage has to be across this resistance? 2 volts. From this point to this point is 2 volts. From this point to this point is 2 volts. This is the same point. This is the same point electrically. If it's connected by wire, there's no loss along that wire. We're assuming not. In a real circuit, there may be loss. We're not there. Okay, so anywhere connected by wire is all at the same voltage. Anywhere connected by wire is all at the same voltage. If this voltage level is 2 above this voltage level, it doesn't matter whether we're looking through this side or this side. Yes, correct, Mickey. Mickey? Correct answer is 2. Turn to your neighbor and discuss. What did Tucker say and why did he say it? Voltages in series add up. Voltages in parallel are identical. Put it in your own words. Ask me a question. These two, I mean, they're two circles. These two are not in parallel. This combination is in parallel with this resistor. Yeah, I mean, look at the bottom of this bean. The bottom of this bean is directly touching the bottom of this sucker. Look at this top of this bean. The top of this bean is directly touching the top of that sucker with no intervening components. Those are the combinations in parallel. That's why I could say the 2 equals 2. Okay, other questions? When you talk to your neighbor, hopefully that reveals parts you're confused about. Ask me a question. Please. Nope. This guy suffers 2 volts. The top one. If that left guy is 1 volt and the middle guy will have to be 1 volt and the right guy has to be 1 volt, yes. Yes. Why say this guy, why red resistor and blue resistor aren't in parallel? Things are in parallel if they touch on both ends with nothing intervening. Top ends are touching with wire. Yes, check. Bottom ends are not touching. There's a resistor in the way. Huh? Trace with your finger. Trace around, and if your finger runs into a resistor, stop. If your fingers can touch from the bottom of one to the bottom of the other, that's parallel. On both sides. There's another trick I'm going to teach you, the highlighter trick. I think I'll teach you later, though. We'll get there later. That'll be next time. Okay, now, series and parallel addition rules. I gave you formulas at the beginning. Let's apply these. I'm going to give you some examples here. I'm going to apply 6 volts of difference, put a 6-volt battery on a 2 ohm and a 3 ohm like this. Now I'm going to apply 6 volts of voltage. Wow, that's a terribly drawn bracket. I'm going to apply 6 volts from this end to this end of the 2 ohm resistor here and the 3 ohm resistor there. What could you tell me about the total resistance in the top case and the total resistance in the bottom case? Think about it, calculate it. Watch your fractions. Again, your challenge now is to find the total resistance. Use the formulas, Luke. Hey, I should define what I mean by total resistance. I'll also call this equivalent resistance. I think the homework system always calls it equivalent. A resistor is equivalent to a circuit if when I put the same voltage on, I get the same current flow. So I claim that 2 ohms series 3 ohms is equivalent to 5 ohms. Hey, how much current flows when I put 6 volts on 5 ohms? 6 divided by 5 is 1.2. Yeah, right? 6/5. Okay, let's see. What happens if 1.2 amps flows through 2 ohms? How much voltage is lost? 1.2 amps, 2 ohms, how much voltage is lost? This should not be hard. I times R, baby. If I got 1.2 amps flowing through 2 ohms, that voltage difference would be 2.4 volts. Yeah. 2 times 1.2, I times R. Okay, if I had 1.2 amps flowing through 3 ohms, what would I have? How many voltages would be dropped? Last time I checked, 3 times 1.2 is 3.6. Okay, what do you notice? The total voltage is still 6 volts. I would have to apply 6 volts, 2.4 plus 3.6 is 6. I would have to apply 6 volts in order to drive the same current through the original circuit. That's what I mean by equivalent. Apply the same voltage, get the same current. It takes this much voltage to get that much current. Note, I had to use the principle that if 1.2 flows in the left, the same 1.2 is flowing in the right, yeah? Okay, now, there is a very common goof here. Muy importante. Préstame tu atención. Please lend me your ears, meine Damen und Herren. 2 ohms, 6 volts. How come there aren't 3 amps of current? Turn to your neighbor and argue. I'll tell you there aren't. It's 1.2 amps. But why? Why? Tell me why there aren't 3 amps of current flowing through this left resistor. Turn to your neighbor and argue. One point two, 6/5. Dr. Wagner, I just want to. Dr. Wagner is my beer evaluator. I presume that we're going to go after beer. I assume, right? That's what that means. Oh no, he's my peer evaluator. Oh, no beer. It's a pun. He's my peer evaluator. He's coming in to say if I suck or rock. Okay, so let's bring it back together. The point that you should have been arguing is whether there are 6 divided by 2 is 3 amps or 1.2 amps. There are not 3 amps. You cannot say 6 volts divided by 2 ohms. Why not? Anyone willing to speak out? Yeah. The total is 5. Exactly. This 6 is not experienced by the 2. The 6 total volts are applied to the total resistance. Exactly. You cannot apply total volts to individual resistors. Not in series anyway. Yeah? Does that taste okay in your heads? With your brain tongues? Ew, that's the most disgusting image ever. I apologize. Okay, show. Show. We got series, we got parallel. What's the parallel equivalent? What single resistor would draw the same current at 6 volts? Use the formula. What's 1 over a half plus a third? 1 over half plus a third. 1 half. Let's write it down. Find a common denominator. Yes. Now it's 1.2 ohms. Hey, that's a coincidence. Yes. Precisamente. Okay, look. Hey, here's a coincidence. 1.2 popped up again. Because of the numbers that I used. Previous is 1.2 amps flows through the series. Now it's 1.2 ohms is the equivalent of 2 plus 3. Please note, by the way, 2 plus 3 is not 5. 2 plus 3 is 1.2. You do not add resistances in parallel. Why not? Why not? Because current has a choice. Current has 2 highways to go through. You get more total current. You get less total opposition to flow if you've got more lanes, right? If I have a freeway and then I put another freeway beside it, I've got choices. The total traffic will be less if I offer more choices, right? So the total resistance gets bigger or smaller in parallel? Smaller. Adding a freeway, adding another lane, you always get less traffic, not less traffic, less opposition, less jams. You're letting more cars through. Remember this, the resistance of parallel branches is always less than the least. Resistance of series, greater than the greatest. If you add numbers together, upstairs, you always get a bigger number. If you add fractions downstairs, you always get smaller than the smallest. Okay, hey, how much current does the 1.2 ohm resistor draw at 6 volts? What's 6 divided by 1.2? 5. 5 amperes. 5 hamsters. Amperes. Not hamsters. Okay, let's look at the original circuit. How many amps are going to be drawn by the total circuit? Google form. How many amps are drawn by the original circuit? Google question what? H? What the H? If your Google form is working, tell me an H. How many amps must be drawn by the original circuit? Turn to your neighbor and tell them how many amps must be drawn by the equivalent circuit. Again, I define equivalent circuit as apply the same volts, get the same amps. The correct answer is 5. As I just said, equivalent means same volts, same amps. Yeah, makey sensey for realsies? Riddle me this, Batman. Does that mean 50-50, 2.5, 2.5 amps? No. Here's a test question. What fraction of the total flows through the 2? Work this out. If you've got a Google form available, this is question I. What fraction of the total current flows through the 2 ohm resistor? What fraction of the total current flows through the 2 ohm resistor? I've told you the total current is 5 amps. I told you that the total current is 5 amps. What fraction of that flows through the top? You have plenty of information to find. Look at this circuit. Find the fraction of the 5 that flows through the 2. Sorry? Yeah. Sorry. One more time, your challenge at this moment, which is a test question, by the way. What fraction of the 5 flows through the 2? How many, what percentage, what ratio of the current in the top resistor to the total current? It is not 2.5 amps. It does not split 50-50 unless the resistances are equal. Hey, how much voltage does that 2 ohms feel? 6. Why? Because it's parallel. How much voltage does the lower guy feel? 6. Parallel, identical volts. 6 volts, 2 ohms, how many amps? We got 6 volts at 2 ohms, how many amps? And if you got 6 volts at 3 ohms, how many amps? Yeah, V equals I times R. If I know the voltage across a resistor and the resistance of that resistor, I could find the current through that resistor. Now tell me this, what fraction of the total flows through the top? Turn to your neighbor and discuss. You need to be able to find a ratio. Aye. Aye, aye, aye. Aye, 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 aye. I win. Again, the question is, what fraction of the total current flows through the top resistor? I've given you the currents in each resistor. You should be able to find this. The correct answer is 3/5 of the total current flows through the total. 5 amps total, 3 amps top, 3/5 is the fraction, yeah? Okay, we have done a fair amount already. There's a bit more to do, but I'd like you to take a few minutes and look back over everything we have done. Look back at your notes today and discuss what have we found and why. Try to give some justification. Don't just memorize this table. Memorization sucks if you don't have a reasoning for it. Memorization is fragile. So turn to each other and discuss why things are true. I'm going to give you guys 4 minutes by the clock. Then we got a little more to go and then we're done. How you feel? Listen. How you feel? Yes. StatMech is beautiful, simple once it clicks, and magnificently challenging to master. Ask. Cut off hours. Ask me on the trip. I'll give you my impression of it. I cannot deduce the entire thing, but I can give you a darn good explanation, not during class. Yeah. I think it'll take about 10 minutes to really get the gist of it. Maybe less. Okay, that's 4 minutes. Again, I beg you, and please, I've got some really good questioners who really are engaging with the class and give me a reason to live. Let me hear from the rest of you. If you're confused, show me where, and I shall make all clear. Ask me a question, particularly if you don't normally, which isn't to say that the usual suspects can't ask. Tell me where you're confused and I shall help. Or I'll try to help anyway. You should ask him about. No, I didn't hear the rest of that. What do you ask? If I ask the ratio of this to that, that's a division problem. The ratio of what to what? The ratio of the top current to the bottom current. Wait, I didn't do 2/5. I did 3/5. I said the 3/5 is the answer. You mean the very last thing I said? The fraction of the total. You identify the fraction of what? The fraction of the total current. If I ask for the fraction of the total resistance, that'd be different. The total, the current here is 3. The total is 5, 3/5. Well, the 2 ohms and the 1.2 ohms, the 2 is the part of the 1.2. I don't think it makes sense to ask about the fraction of the total. 2 is a part of the 1.2. I don't know. I could talk about the fraction of the total voltage in the top, though. Here, reflect on this. That's a worthwhile question. What fraction of all the 6 volts are dissipated in this 2 ohm resistor? I got 6 volts burned. What fraction of that is burned in the first dude? In Mr. 2. There are 6 total volts. How many volts are lost in the first sucker? 2.4. How do you know? I've lost you guys. Lots of blank faces here. Okay, how do you find the total current flowing through everything? What's the total resistance? 5 total ohms. If I've got the total voltage and the total current resistance, I could find the total current, 1.2 amps, right? Remember, 1.2 amps flows through left and 1.2 amps also flows through right. Then if I've got 1.2 amps and I've got the resistance that 1.2 amps is flowing through, what's the voltage drop? IR, 2.4 volts dropped across the first. How can I immediately jump? How can I immediately jump to, Kyle, no. You only answer the question in the Google form when I say answer the question in this space. Don't answer every rhetorical question I give you on the Google form. Here's a hint. I will usually write the letter in a little box if you're supposed to be answering it in the Google form. Okay, let's go back. We deduced from the total voltage, total current, total resistance, 1.2 amps flows. 1.2 amps flowing through 2 ohms, there is a drop of 2.4 volts. The question is, what fraction of voltage is dropped in the first resistor? 2.4 over 6 is what? 2/5? 0.4? 40%? Yeah? You feel better about that? Identify what I'm talking about. What fraction of this is that? And then find the this and find the that. Well, the that is given at 6. How do you guys feel? How do you guys feel? Better? Worse? About voltage and current in particular? Like a 3? Yes, yes, they will not always be mirrors of each other. Hey, let me ask you, give me a finger. Give me a finger based on how confident do you feel about voltage and current? I can't see the Google form for most of you. 5 is voltage and current are clicking. Stuff is making sense. You don't have to be perfect, but tell me if it's making perfect sense. 5 is perfect sense. 4 is 3 is about the same as the beginning of the class. 2 is I'm more confused. 1 is fuck you. Give me the finger. Okay, I'll take it. More sense. There's a saying that goes, practice makes perfect, and it's a lie. I've been practicing stuff all my life, and I still make mistakes. But it is true that practice makes progress, and I'm glad to see that things are looking better. Okay, there is one more thing, and then I'll let all y'all go. There's one more thing to discuss, and that is the direction of current. We're going to do some current problems talking about direction as well as magnitude. We've talked about, solving for number. Let's talk about which way. Close your eyes and imagine this. Imagine this. There is a peaceful stream on the side of a mountain. It rains on a mountain, and the water makes a little stream on the mountain. Does water seek to go to higher altitudes or lower altitudes? Duh, right? Water go down? Okay. But what about the water cycle? When sun shines on ocean, what happens to the water? Does it go up or down? It evaporates, it goes up. Why does it go up and then go down? When there's an external source of energy, the sun heating, that can drive water to where it don't want to be. When it rains, it is releasing its potential energy, right? That's what happens in in any circuit. If you are supplying energy to charge, you can get it to flow uphill to higher voltages. On the contrary, if you are letting the current go where it wants to, it will naturally seek to go downhill from positive to negative. What direction does current flow through a battery? A battery is supplying energy to the charges that flow through it. Does charge flow from the minus to plus or plus to minus? Minus to plus. You are supplying energy. The battery is turning stored chemical reactions into electrical energy. The battery is the sun. The battery is the sun part of the water cycle. You're delivering electrical energy. You're evaporating water and putting it in clouds. Water is going where it doesn't want to go. Electricity is going where it doesn't want to go. Positives don't want to go towards other positives. So in a battery, charge is pushed from minus to plus. In a resistor, current will always flow from plus to minus. Now there is one exception to what I just said. What happens if I charge a battery? Is that battery giving or taking energy? Taking energy. If you recharge a rechargeable battery, current is forced from plus to minus. That's how you recharge it. You are dissipating electrical energy inside the battery, which is, if you're doing it right, charging it. You are putting electrical energy into chemical energy again. Write this down. Write this down. Charge always flows from plus to minus in a resistor. Just like water always flows downhill. A battery normally drives current from minus to plus, pushes it where it doesn't want to go. What about a water pump, by the way? Does a water pump push water uphill or downhill? Water pump can push water uphill, right? An external source of energy is giving the water potential energy. A battery that is acting normally pushes charges from its minus to its plus. What about if I recharge the battery? What if I force water backwards through the pump, making it a generator? Water is going from plus to minus. Battery charging circuit, you have to drive current backwards through the battery from plus to minus to store energy in it. Let's do some applications of this, not just spoken words, but see an example. No, here, just two resistors. I'm going to give you the plus and minus ends of these resistors. The normal resistor symbol does not have pluses and minuses on it, okay? The normal resistor symbol is just the squiggle. But to find the direction of the current here, I'm going to tell you the plus end has higher voltage than the minus end. Don't always draw this. This is an aid in this particular problem. Gina, sure, except everyone is getting free points today. The question is, oh my God, my son was so cute. When he was 4, he would mimic his professor father and say, the question is, and then say something random. The question is, I'm hungry. It was so freaking cute. I never got it on camera. The question is, which way does current flow in the top wire and how much? This is a homework question, by the way. Not this exact problem, but something very similar. Question is, which way does current and how much? No, I should put the squiggles. More circuit, more circuit, more circuit. Who's stuck? Or guck, as my baby now says. You're guck? You're guck? Okay, here's how to solve this. First, if I know 4 volts applies to 2 ohms, what much current flows? What magnitude? 2 amps, V over R. Which way does it flow? Does current like to flow uphill or downhill in a resistor? It releases its energy. In a resistor, on a hillside, water flows to lower elevations. What about this resistor? Which way does it flow in the bottom? From plus to minus, always in a resistor. Yeah? No? Question? How much current flows? 18 volts, 12 amps. 18 volts, 12 ohms. 18 divided by 12. Mental math here. 1.5. Okay, I've got 2 amps approaching this dot. I've got 1.5 leaving this dot. There must be another 0.5 amp leaving this dot. Correct answer for the question I posed was 0.5 amps up. Huh? 2 are coming, 0.5 and 1.5 are leaving. Say it again. Oh, the rest of the circuit. The rest of the circuit, there's got to be some batteries somewhere. Yeah, there's a battery with a minus side on top somewhere. Yeah. It does. Because here's the positive end and here's the negative end. It is. You should be. I hate questions, is what I never say. You want another? Well, tough. You're getting another whether you like it or not. Such to suck. I'm going to switch the signs there. Plus on the bottom, minus on the top. Apply a higher voltage to the bottom of the resistor. I zap his bottom. What happens? Work it out. Just like a constipated mathematician, work it out with a pencil. Sorry. Not sorry. You got it? 3.5? Okay, time's up. 12 volts, 18 amps, 18 volts, 12 ohms. How much current? It's the same numbers. 1.5 amps, up or down? Two amps and 1.5 amps enter. How much must leave? And I broke my nail. So excited. Last question. You get this right, you get to go, yeah? Think carefully here, because I have not drawn this in the same fashion as normal. Tell me the voltage difference between those 2 points. How high is this open circle relative to the closed circle? If I put a voltmeter from the open to the closed, what would it read? I told you that the top resistor drops 4 volts going that way. The bottom resistor drops 18 volts going that way. What's the voltage difference there to there? If I take a voltmeter And do that. What's it read? You give up? Okay. Here's how I do this. Voltage levels, this is a profound statement that we'll discuss much more later. Voltage levels, there is no such thing as absolute zero voltage. You can define any point to be zero. I'm going to just choose this point to be called 0 volts and reason based on that, okay? I'm going to define this point as electrical ground. So if this point is at 0 volts, how much voltage is here? Negative 18, yes. Look, if this is the plus side and this is the minus side, voltage is going down in this direction, right? If you start at 0 and go down by 18, where do you end up on the number line? That level, that wire is at negative 18 volts. Riddle me this, Batman. Is this higher voltage, lower voltage? Am I going up or down to negative 18? I'm going down to negative 18. Okay, so if I go down to negative 18, I go down by how many? If I decrease by 4 and end at negative 18, what did I start at? Negative 14. Look, check it. Negative 14 minus negative 18 is 4. This point is 4 volts higher than this. Negative 14 is 4 greater than negative 18. Negative 18 is 18 lower than 0, yeah? Look at the directionality of the voltages. So if I hooked a voltmeter up like this with the red lead this way and the black lead this way, it would say negative 14. You get to go early! I love you all because you are the best.